hopefully everybody can hear me okay. If you can, just drop me a message in the chat just so we can check that the sound is good. But welcome to this session. Today we're going to be talking about how we can tackle timing analysis and how we can get started with our FPGA design, and hopefully how we can help get a nice timing closure from that. Like I say, if somebody could just drop me a message to see if you can hear me okay. I'll just pop something in the chat. Perfect, sounds good. We'll crack on. So as we go through this, it's going to take us about an hour to get through. So as we go through it, please just sort of any questions you want, just drop them in the chat, and I'll try and come back to them as we go. At the end of this session, what I'll do is I will upload this all onto my website, into our YouTube channel, and I will put the links to the slides there. And although mostly this is going to be sort of talking around slides and such like, I'm going to show you a couple of Vivado projects as we go through it. So I'll upload those Vivado projects as well to the GitHub such that you can go and grab them and take a look and start running through those as well, which should be hopefully quite useful. So any questions anyway after the event, my email address is about to be on screen. So feel free to just drop me an email or ask any questions that come from that. So without further ado, let's make a start. And without one of the biggest challenges that we see, and I see this quite often as an FPGA consultant when people give us designs or when they come to us for help, is how they're going to be able to achieve how you're going to achieve timing closure and make sure that that design works. Obviously, there's a lot of constituent parts to achieving timing closure, so we'll need to think carefully. We'll need to think carefully about it. Hopefully, this session is going to give you some tools and some useful points, such that you can go away and start working towards timing closure on your own. So what we're going to do, we're going to run through these objectives. We're going to talk a little bit about what is the concept of timing closure and how do we get there. We're going to talk a little bit about clocks and clock domain crossing, and then we're going to talk obviously about constraints. The main bulk of this, though, I hope we're going to be working through an example. I've got lots of, in terms of time, I've got lots of slides that show that, but I've also got the projects open so we can switch backwards and forwards between the projects, and we can take a look there and we can run through those projects. So what are the things that we have to do? Obviously, is we want to achieve timing closure, and it's one of those things that we need to think about. Like everything in engineering, you know, the earlier we think about it at the beginning, the better and easier it is to help us when we get to the end. So one of the key things we want to do is we want to make sure that we've developed our RTL in a sensible way, in a sensible manner, to help us best achieve that timing closure. So a couple of weeks ago, maybe 2 weeks ago now, we did a webinar which you can find on our website about how to write RTL for better timing performance. So if this is new to you, I'd suggest you go perhaps take a look at that as well and see what we can do. But essentially, what we want to do is at the end of this, we want to make sure that our RTL design operates at the timing parameters that we've defined for it. So it operates at the clock frequencies that we've defined. The interfaces are nicely timed, and we're safely transferring data on and off chip, as well as processing it on chip at the clock frequencies that we want to. And this can be relatively simple, or it can actually be quite complex. And if we don't think about this right from the beginning, it's going to become quite time consuming. And it's going to be quite painful. Now, a lot of the times, it can also be very difficult. And if you get the constraints wrong, as we'll talk about in a little while, that can lead to your design taking longer to implement in Vivado. So it's better to get the constraints right and the approach right, and then it should hopefully flow through quite nicely. So at a very high level, at a helicopter view, what do we expect from our timing closure? So we expect from a timing closure that all our active clock pins are reached by a clock definition, that all active endpoints have a requirement that's placed upon them with respect to a defined setup and hold or clock. What we ideally want to do as well, we want to make sure all input ports have input delay constraints so we can safely capture the data and work with it. And sometimes, depending upon the speed and the frequency of those, we might need to even, we might need to go very complex on that and start looking at the tracking, the skew, and such like on the PCB. Similarly, for the output ports, we want to make sure that all of our output ports have a good constrained delay on there also. The key thing as well, obviously, is not everything's going to be perfect, not everything's going to be right. So there are going to be some timing exceptions that we're going to want to define in our design. This includes things such as, false paths, multi-cycle paths, different clock groups, all of that information that we want to provide to the tool, and that they're timing exceptions that we're telling the tool. Actually, in this case, there's an exception for it, so we don't need to focus on this too much. So timing success for us as FPGA engineers, it's relatively straightforward. We're looking for a setup or recovery time with a worst case negative slack of greater than 0 nanoseconds, and a total negative slack of 0 nanoseconds, because obviously we don't want any negative slack. Similarly, for the hold or the removal time, we want to make sure that we've got worst case hold time of greater than 0, and the total worst case hold time of equal to 0 also. So we don't want any failing timing cut. We don't want any negative numbers there. Essentially, that is the main thing. And we also want to look at the pulse width to make sure that the worst case pulse width and the total failing pulse width is equal to 0. Relatively straightforward to say, and it's like a lot of these things that I get told off by my engineering team. It's like, hey Adam, you're saying it's simple, and obviously there's a lot of effort and a lot of engineering involved in getting to that position that we're perfectly clean and held in. And what we're going to do today when we get to the example is we're going to take a look at how we can do this. We're going to create what's called a baseline timing closure, or work through a baseline timing closure on a example design that we've created. So by the end of today, hopefully you'll understand how we can get a little bit closer towards those numbers there. So it's increasingly a challenge. Oh, that's a good one, Jimmy. So somebody's just asked a question. So I'm going to jump between talking about the slides and answering the questions to make it a little bit more interactive and fun. So Jimmy's just asked a question saying, since timing success is a byproduct of your constraints, how do you recommend developing reasonable constraints? So if I can ask you to bear with me, Jimmy, that's exactly what we're going to be doing in a minute. We're going to talk a little bit about what clocks are, clock domain crossing, constraints, the types of different clocks in Vivado, and then we're going to work through how we can get that baseline timing closure. And that baseline timing closure is going to give you a baseline set of sensible, reasonable constraints that we can put in into our design to help us achieve it. And one of the key things that I want you to take away from this is we don't just write our code and click the generate bitstream button if we want to get this done properly. So there's going to be several stages as we work through it. So why this is a challenge is because we tend to find our designs, and I'm a big fan actually of the Wilson Group FPGA survey, because we tend to find our designs have several clocks in them these days, and they may be synchronous clocks or they may be asynchronous clock domains. So it's relatively easy to end up with 3 or 4 different clock domains in a design. If we think about our MPSoC type devices that we have, or our Zinc type devices, you can get to the 3 to 4 clock domains very simply. You may have a AXI light interface coming from the processor system to configure your IP logic. Typically you run that relatively slow. You might have a data processing pipeline that you run relatively quick, so that's 2 clocks already. And then you may have some source synchronous interfaces or different outputs that require different clocking domains. So you can end up in the 3-4 clock domains relatively easily. And we have to think about these clock domains and how we work with them, and we'll touch on that in a little while about how we tell Vivado what they are. So one of the things, I'll come back to that question, Michael, in a second once I've congested what actually it is. So Ahmed, yeah, the slides, everything will be available. The slides, the demo designs, the recording of the video, it'll all be available on my website later on, about 20 minutes after this webinar finishes, once I've downloaded it and uploaded it. So if we don't get these constraints right, actually, they can have a big impact on our design. If we don't get our clocking right, it can have a big impact on our design. You know, a lot of FPGAs run behind schedule. I'm glad to say to my clients, see, it's not just me that runs behind schedule, everybody does. But a lot of these have a non-trivial bug that leaks into production. And the root cause of a lot is either logic, as you would expect, a functional issue, or a clocking issue where something's not quite right with the clocking. And so it's some sort of timing related issue that's snuck by, and we've got to get to the bottom of it. Typically, this might be a clock domain crossing issue or something like that. So let's start at the beginning and talk a little bit about clocks in our FPGA design. So they are synchronous. So obviously we want to design our FPGAs to be synchronous, which means we need to leverage the clocks that are coming into the FPGA. Now, we don't just use the clocks on any old pin on the FPGA. We want to use them on dedicated pins because they're high fan out. And obviously the manufacturers of these devices have thought about this, and they put clocking resources within the FPGA that we can use to help us get through the design. And make sure that we can achieve timing easily. So how we do this is we want to make sure that we put our clocks on dedicated clock pins. We want to try to, wherever possible, think about the clock regions that are in the FPGA as well, and make sure that we try to constrain those regions as best we can, because within each region we've got configurable logic blocks, we've got DSPs, we've got PRAMs, etc. Now, when it comes to working on our AMD devices, we've got on the UltraScale and the UltraScale Plus, we have the global clock pins, and these give us access to the entire FPGA network across there. All of the clock domain, all of the multiple regions that are in there, all of the resources that are in there, we can quite easily, by putting a signal on that clock domain, we can quite easily reach all of the resources within the FPGA. On the 7 series, it's a little different. There are clock capable pins, which are restricted to a clock region and its surrounding clock regions, or global clock pins. But these are things that we really want to try to make sure that we're using. And of course, if we're doing things like DDR or DDR4 or anything like that, there are some special clock pins associated on each I/O bank to allow us to do that, such as the byte lane clocks and such like, which we're using in memory applications. But we're not going to worry too much about those. We're going to focus our discussion and our example on just on general normal clocks that come in. So somebody just asked a great question about, could we exhibit why paths that are too fast can cause an issue? So there's several reasons for that. So we could have races in the logic if it's going too fast. It can also, it depends upon how we've done our design. If we're over constraining our design as well, we can be making the placer, the router, we can be making that one work harder and get that. So Michael, typically there are, if I go back to the other slide, I think there are 24 routing tracks in each path. So each region, I think, can get up to 24 clocks, either generated internally or externally. When it comes to working with these clocks, and this is really interesting. When it comes to working with these clocks, we want to take these in through the clock cable pins, and then we want to connect these things to things such as clock buffers. And if we put it to a clock buffer, obviously that clock buffer then connects into the routing, and away it goes. If we want to do anything specific with it, more like thinking about, for example, multiplying up clocks, dividing clocks, or things like that, then we can use one of the clock management tiles, which gives us a multi-mode clock manager and 2 phase lock loops. So using those, we can multiply up clocks, we can divide clocks, and we can kind of achieve optimal clocking that we want within there. Now, interestingly, I wrote a blog this week on when you might not want to use outputs from the same PLL and when you might want to use some of the functionality that comes with some of the clocking buffers and the clocking capabilities that are used in there. The main clocking resource that we see often and that it forms the core of actually is the buff G control. And this allows us to drive the routing, the distribution resources. It can even seamlessly switch between two clock networks. So if we've got a fast clock and a slow clock, for example, say we want to use a lower clock when it's not being actively used to reduce the power dissipation, then we can switch it easily and seamlessly using the buff G control. Now, this buff G control, it forms the basis of many other different macros and primitives that we can use, such as the buff GCE. Now, for example, the buff GCE is able to divide clocks as well. So it can't do the sort of non-integer division, but it can divide your clock input by a power of 2 or 4 or 8 or so on. And that can actually be quite useful. It is. And that's the nice thing about it, that buff G control, it's entirely seamless. There's no glitches. There's no nothing, Jimmy. It's really nice to do. I think I've got a blog somewhere where I give an example of how to use that and how to do the switching between two clocks. But it's a really nice feature in there. And you can do, like I say, you can do that if you really want to have like a high-speed processing clock, but say it's man-mounted, man-portable. You put it down, and you can detect that it's no longer being used, so it can switch to a lower frequency clock. To keep some logic alive and save you some power dissipation, or you could do it with sort of safety criticality type approaches. So the 7 series guide and the ultra-scale clocking guides are really useful things to read. You know, it's really odd. The manufacturers want you to be able to use these devices and use them well, so they put a lot of really good information into their user guides, particularly the clocking user guide. So with our clocks, we need to be able to tell information to the implementation tool how to go away and and implement this design that meets timing. So how we do that initially is we provide some constraints to the design. So we tell the design, we tell Vivado what clock frequencies we want to operate at. We can tell them to run, for example, just during synthesis or place and route, or we can use those for pin placement. So we'll find two groups of constraints: the ones that are used for timing, or the ones that are used for placement. By default, the AMD ones, they use an XDC format, which is based around the industry standard SDC format as an extension to that. So as you'll see as we go through the example in a minute, when we define our constraints, what we want to do is we want to define these in the following order. So the first thing we want to do is we want to define any timing constraints. So we need to define the timing relationships for correct operation. Once we've defined the timing relationships for correct operation, the next step is to be able to tell what any timing exceptions are. So for example, if we have clocks that are asynchronous to each other, we want to provide that information and say, hey, these clocks are asynchronous to each other. Don't try to find a common phase, find a common period, because it's not going to happen, and it's going to burn a lot of implementation time. And we need to define them in this specific order, because obviously we can't, if we've not defined a timing constraint, we can't define a timing exception to that constraint. So we have to do them in this order. And then finally, we might have implementation constraints, just as I was talking about, where we might want to talk about the pin. At the simplest level, it's the pin out, the pin IO allocation. But actually, that might also include things such as where we want to relatively place macros, relationally place macros, or P blocks, or things like that. If we're really getting into the difficulties of trying to achieve some quite challenging timing closure. Where's my mouse go? So just to make sure that we're all on the same page with this before we move through, what we really want to do, obviously, is we want to make sure that our input signal is stable for the setup and the hold time, And also we need to take into account the clock to output, that we need to consider that there will be a clock to output time as well. Such that we can see the we can take into account that change from when the clock is to the data actually becoming stable. So the setup time, the hold time, the clock to output time become increasingly important in our design analysis and our timing analysis, particularly when we're doing I/O type applications as well. When we're trying to achieve I/O constraints and I/O timing, we really need to pay attention to those. Not that we don't when we're working internally, but when we're working internally, the tool's going to do a lot of this for us. Externally, we've got to do a little bit more work, do a little bit more concentration with our spreadsheet. So just to give some understanding of how Vivado views clocks, so it's going to group them into one of three types. It's going to say that it's a primary clock. So if it's a primary clock, then it's going to be entering through an I/O pin. If it's a generated clock, then it's going to be generated internally by the PLL or something that we've done in a design. For example, dividing it using a buff G control or using a flip flop or something like that. We also have this really nice concept that we can have a virtual clock. Now, maybe I'll write some blogs about virtual clocks or something to explain the concept a little bit more, but they're not really attached to anything that we're in the design. It's by its name, it's virtual, but it allows us to analyze the design netlist, particularly at the I/O, to work out that our timing is safe for bringing data on chip and off chip. And we can create these clocks with the command telling with the XDC command below, telling it to create the clock, the period, the name, and the period and the waveform duration. So it's relatively simple, as you see as we go through. But if it's a little bit tricky, we're going to use the wizard anyway when it comes to that. As we're going through this as well, we're going to see elements in the timing report, which is going to talk about the launch clock, the capture clock. So the launch clock is obviously, that's associated with the source that launches the data into the network, and the capture clock is the one that captures that data at the receiving flip-flop. They could be, as we're going to talk about briefly in a second, they could be different clocks. You know, that we could be doing some clock domain crossing, but by and large, we generally try to keep them all at the same clock, which makes sense. Obviously, where the complexity comes in is it's got to pass through the combinatorial logic, the clock net. There's going to be skew in the clock network, and then there's going to be routing delays within that combinatorial logic as well. So the faster our clock goes, you know, the less time we have for our signal to pass through the routing and pass through the combinatorial logic. So just to make sure that we're aware, obviously, that hold time, we're going to make sure the hold time is making sure that the data is stable after that clock edge. And we're going to need to be very carefully considering the launch and the capture clocks are different, particularly to make sure that we get the hold and the setup time. Now, Vivado is going to do all this analysis for us when we ask it to do a timing report. And it's going to run through and it's going to analyze the setup and hold times. The exception to that, obviously, is we need to tell if we're doing I/O type stuff. And it's going to give us a result that's going to give us what's called the slack in the design. Now, as we said earlier on, in the timing closure, you know, positive slack means that the register will not clock in a wrong value or go metastable. If we have negative slack, then that means metastability. Corruption is an issue because we've got a timing violation in the design, which is what we're trying to avoid. Now, along with the primary, the generated, and the virtual clocks, Vivado also defines clocks as falling within one of three categories. So we can have a synchronous clock. So these are clocks that are going to have a known phase relationship. So if we take a 100 meg clock and divide it to 50 megahertz, there's a known phase relationship there. We can find that relatively easily, and because they can share a common root clock, Vivado can safely do that timing analysis. We have asynchronous clocks, and these are where there are no predictable timing phase relationships between the two clocks. And that means it's very important that in that case we define those as a timing exception, because if we don't define those as a timing exception, what will happen is Vivado will try to find a common period over a large number of clock cycles, over 1,000 clock cycles. And if it can't do that, it will go with the best information that it could get from doing that unexpandable clock, so over that 1,000 clock cycles. Obviously, there's no guarantee that that information is correct at that point in time that Vivado is based off, but it's doing its best. So what we really need to do is we really need to define not only those clock constraints, but those timing exceptions as well, because by default, Vivado makes sure that Vivado assumes that all clocks are related to each other and that they're all synchronous unless we tell it otherwise. So let's just quickly talk about clock domain crossing, very, very quickly actually. But within the same clock domain, if we have the same source or an integer multiple of frequency, so we can find that common clock domain. If it's not coming from the same source or an integer multiple, then it's a different clock domain, and we have to do clock domain crossing. Obviously, even if the frequency is the same, you don't know what the phase relationship is, so we've got to do that clock domain crossing. Now, to help us do that clock domain crossing, and we should put this in before we try to do any timing closure or anything like that, which is why I'm mentioning it in this webinar, is we should try to understand our clock architecture, our clock design before we move forwards, and make sure we put the right structures in place. After you've run synthesis in the Tickle script, if you're not sure about clock domain crossing in your design, after you've run synthesis, you can type in report CDC and it will report you the clock domain crossing, or you can report the clock interaction report as well, which will give you a good indication of what's going off in that domain in your design, and how the clocks are interacting with each other, and whether they're timed, whether they're timed safely, whether they're untimed, whether they're unsafely timed, whether there's no timing relationship between the two. That clock interaction report is really good. I think actually we've talked about this. If we violate the setup and hold times, it's part of the reason why we're doing it for metastability, for asynchronous clocks, and for timing closure. We will get the flip-flop to go metastable and lead to corrupt rate. So someone's just asked a question: are clocks with the same source but non-integer ratios synchronous in Vivado? No, they wouldn't be, because you're looking for a common phase relationship, and if they don't have if they've got a non-integer relationship, then they don't have a common phase relationship. So it should be treated as asynchronous. And actually, I wrote a blog this week on saying even if things are synchronous, then to remove clock uncertainty from the PLL, you might want to look at using the buff G controls at really high clock frequencies to give you a little bit more margin when you try to achieve timing closure. So if we do think we've got asynchronous clocks in there, before we get to the point of developing our FPGA application, before we get to the point of trying to get timing closure in our FPGA application, what we should do is we should leverage clock domain crossing techniques to make sure that we safely cross the information from one clock domain to the other clock domain. We can do that using a two-stage synchronizer, gray code synchronizers, handshake synchronizers, pulse synchronizers, or even asynchronous FIFOs. They're the common techniques to do this. And rather helpfully, AMD provide several techniques that we can also use, and provide several macros called in the Xilinx parameterized macro file to do that CDC crossing. And they'll also help us do the crossing of resets as well. So we have to be very careful about moving from moving resets and making sure our resets are synchronized as well. So we might need to look at using an asynchronous reset synchronizer or a synchronous reset synchronizer. Like I was saying, the Xilinx parameterized macros are ideal for this. They're really good for doing it. They'll put you the CDC structure into your design. And then the implementation tool will know that's what you need to do. Now, that's a good point, Paul. You have to use the async reg. If you're doing it by hand, if you're doing the clock domain crossing by hand, you have to use the async reg. As I understand it, and I might be wrong, I frequently am apparently, we can use the Xilinx parameterized macro. And if you use the XPM, it doesn't, you don't need to do that async register because the tool understands that's what you're trying to do. So William, that's a good question about the different strategies depending upon the frequencies of interest. If you're passing data buses, obviously, then yes, because you've got to make sure that obviously you're not going to, if you use a FIFO and you're going from a fast domain to a slow domain, that you never can't write the data into the FIFO. Similarly, if you're transmitting a pulse from one clock domain to the other clock domain, it can make a big difference as well. But the XPM provides a lot of structures that can help you do that. So pulse synchronizers, FIFO synchronizers. And again, it's back down to sort of being an engineer and working through how we want to do that clock domain crossing. So I really would recommend taking a look at like user guide 953, 974 and seeing what's available in those XPMs, because they are actually really quite useful. So we've talked a little bit about like why we want to do time enclosure. We've talked about sort of clocks in FPGAs, and please use dedicated clock lines, the clocking resources that we've got in the MMCM, the PLLs. We've talked a little bit about constraints and how Vivado views clocks. And then we've talked a little bit about clock domain crossing, just to give you some ideas that might be necessary. It's not going to be necessary in the example we've got today, but I'd like to get as much information as possible. And so we're going to talk now about the time enclosure approach that we're going to take over the next 30 minutes or so. And what we're going to do is we're going to achieve a time enclosure called a baseline time enclosure. And that baseline time enclosure is going to allow us to get a simplest set of constraints possible for our design. We're going to not worry about the I/O for the time being. In this application, we're not going to worry about the I/O. We're just going to look at getting time enclosure for the internal design. So what we're going to do is we're going to go through several stages of the design to do this. But we're going to not just click the button. Like I said, we're just not going to click the button and wait for the bit stream and then start trying to do some debugging. What we do is we do the synthesis first. Once the synthesis is done, if the timing constraints aren't already defined, we can define the timing constraints. And then we're going to report the methodologies to make sure that we're not violating any of the methodologies or any of the basics. So we're going to write our RTL, we're going to write some timing constraints, and we're going to make sure that we've done everything in that RTL to best align with the Xilinx AMD methodologies. Once we've done that, we can run the optimize of the design. And if we've run the optimize of the design, we can then run the report timing summary. Now, this is an estimate at this point, but it's going to give us some worst case negative slack that we can go away and look at and investigate and try and get to the bottom of it. Once we're happy that we've addressed any issues that come up from this optimization stage, and it's going to be an iterative approach. We're going to make changes and changes and changes as we go through, but we're going to be running the CD, we're going to be running the synthesis and then the optimize. But hopefully it won't be that iterative, as I'll show you in a minute. Once we've addressed any issues that have been identified during the optimize phase, we're then going to do the place. We're going to then let the tool do the place. And if there's any negative slack, we're going to address that. If there's any large hold time failures greater than minus 0.5 nanosecond, we're going to address that too. If they're lower than that, we're actually going to not worry about it at that point in time, because the router is able to resolve. It's a typo, Ahmed. I'll correct that. It should be it's the hold slack, but the worst case hold. I will correct that. And then once we got to the root design, we'll let the root design run, because the router should be able to address some of the hold time violations that are less than 0.5 of a nanosecond. So hopefully, my example, you're going to see all this. And by the time, obviously, we get to the end of the routing thing, we've got a timing design that gives us a baseline timing closure. Yeah, so WNS is worst negative slack. and WHS is worse hold slack. So we're going to do this. We're going to follow through this timing violations, and we're going to take a look at what we want to do. So Catalan, you can do CDC and RDC verification using Vivado. There are other tools out there that can help you do it, but it's entirely possible to do using Vivado. Yes. So if we take a look through this, when we're looking at our design and we see issues that have WNS or WHS, we need to categorize where the issue is such that we can work out the best way to go away and attack it and tackle it. So we might see that we've got a high cell delay, in which case we might need, as you'll see in the example in a minute, we might need to modify the RTL, we might need to look at pipelining, we might need to look at removing constraints that we previously had in before. Yeah, so the Synopsys, I would say the best tools for CDC, RDC are the Synopsys tools and the Blue Pearl tools. We use Blue Pearl Visual Verification Suite, but people use different tools depending upon what their companies and budgets are. So we have if it's a high cell delay, then like I say, we might have to modify the RTL. If it's a routing delay, then we might have to look at the fan out, the placer, how we do the congestions, whether we put any pipelining in there or placement flip-flops in there. And if it's a high clock skew or clock uncertainty, then we might want to look at things like I wrote a blog about this week, actually, which about the third time I've mentioned that for some reason. We might want to not just use all the outputs of the MMCM. We might want to take an output from the MMCM and then divide it using a buff GCE or a buff GCE divider, for example, to remove some of the phase error that can contribute to the clock uncertainty in there. So that's what's going to take. That's the approach we're going to take. We can take a look at the high cell count, the route delays, all the there. As far as I'm aware, these steps are available in project mode and non-project mode. We're running through the same processes as we go through it, whether you're doing it in the GUI, as I'm going to show for the example because it's more illustrative, or whether you go through a scripted in project or non-project mode. All these steps are still there and viable for it. One of the things as well that's going to be useful as we go through this is to leverage the reports and make sure we get the quality of results, the quality of results suggestion, and the design analysis report. Use those results to help you with your design as you go through it. So a couple of things that we'll talk about just very quickly, otherwise we're in danger of running out of time. If we see logic delay, what we should be looking at in our design is, are there many levels of logic? Is there anything in there that's preventing that logic optimization? And is there anything in there that's got a high logic delay, such as a block RAM or a DSP, where we might need to pipeline it properly, or have we put pipelining registers in there? If we've got net delays, like we're just talking about, we can look at high fan outs on the paths. We can look at making sure if we're using P blocks, are the P blocks far away from each other. We could put in pipeline registers. We could put in placement wrappers around the tool, as we were talking about in our previous webinar a couple of weeks ago about designing RTL. And then finally, for the clock stuff, we can look at, is there any CDC issues? We can look at making sure that the clocks are synchronous or asynchronous. We can make sure that we've got things such as the buff, as I was just mentioning, the buff GCE to do that division for us instead of MMCMs. So let's take a look now at a simple example, and hopefully we'll get through and show it all working as a baseline timing example. What we're going to do is, I have a Hackster project. The Hackster project takes a RS-232 input from a Raspberry Pi Pico, converts it into a AXI protocol, and then allows you to access the AXI network. This Hackster project's been around for a while. So I thought what I'll do is I will take this project as it's shown there, and we'll make some modifications to it, and we'll try and see how fast we can get it. So we have a couple of custom RTL blocks here that we've written, a UART and a protocol, and then we've got some AMD IP. So this is a really nice example, because what we're going to find out as we go through this, we get some timing issues in the RTL that I've written, and some issues around the IP, which gives us a nice way to go away and look at and think about. So if you want the project, it will be linked from here. It's originally it was designed to run at 100 megahertz. I think originally it was running on a Arctic, or a Spartan or something. And then I decided for this project that we would target it at our new Spartan 7 tile, which has got a tiny little Spartan 7 25 device on it. And I wanted to, and I thought we'll make it run at 200 megahertz, to give us some challenge to do that. So I made the changes to the project, and then we synthesized it. Initially, I followed through the approach that there were no clock constraints in there. So once we've synthesized the design, I opened the timing constraints wizard. Should have put the constraints in beforehand, but I wanted to flow through the exact approach. I opened the timing constraints wizard in the synthesis view in Vivado, and we set the target frequency to 200 megahertz. As we're doing a baseline timing closure, and I'm not too worried about the I/O timing, at this point we just clicked on skip to finish, and we had our timing constraints in there. And if you want to, this will show you the create clock, and you can then jump to the timing constraints in there. What we did then is, with the design in the Vivado synthesis view opened, is once the synthesis had been recompleted, because I had to, if you define the constraints, you've got to rerun the synthesis. I ran the methodology report, and it came up really quickly with a couple of issues that were missing in there. The first one, missing input or output. The second one, sorry, missing input or output delays. That's fine because we've made a conscious decision that we're going to ignore them. This other one, though, ClockNet has I/O driver, not a clock buffer. That's a little bit more concerning. So if we look back at our block design, we'll see the clock just comes straight in here, straight into this RTL module here. So if we go away and look into our design, what we need to do is we should put in a buffer, because there was no buffer being instantiated. So we go back to our RTL design, and we put a utility buffer in this to give us a clock buffer, to put the buff G in there. Run through the synthesis again, run the report for the methodology, and we can see this time that we've got I/O timing issues, but now we've got a buffer in there. We could have put this in the clocks, we could have put this in the RTL, and that would have been fine. But it makes more sense to show the concept here in the IP integrator, just to teach us to make sure that we put one in. So with that, we can take a look then, and we can run through, with the synthesis completed, we can run through the optimization. So we can, in our Tickle console, we can run the opt design command. That'll take a few seconds. It'll run through, and once completed, we can open the timing constraints, the timing summary. So if we do this, and it's almost like Blue Peter. If I go to the right one, here's one I did earlier. If we do that, we can open the timing constraints. We can run the timing estimation, timing report, and we will see that we have 10 failing paths here. And these paths are related to the Smart Connect to the block RAM and something within my RTL. Perfect. Couldn't have timed this any better for an example. So if we just zoom in this schematic a little bit, what we can see is here we have the Smart Connect that's connected to the VRAM controller that's connected to the VRAM, and we have a register over here, all the way over here, and then as it goes through this long path, passes through some lookup tables. So there's four levels of logic, runs all the way through here, and eventually terminates in this flip-flop down here. It can't do that. It can't pass through all that logic and routing in the time that's available. So you can see here we've got a logic delay and a routing delay. The routing delay dominates actually. So we need to think about what we can do to address that. If we click on the other example of timing, then we see that it's entirely contained within our within the AXI protocol block I've written, and it's in between a counting of data as it's stored into the logic. We'll look at the code exactly in detail in a little minute. But the first thing I wanted to do was think about, well, you have to address these problems as they come up and they're head on. So the first problem I decided to tackle was the Smart Connect in the RTL, and how I went away and looked at that. If we want to, we can run the timing optimization report. We can see each of the reports. We can see all of the paths coming through it. I tend to prefer to kind of look in the schematic and then read the reports, because I'm quite a visual engineer. But now we've got choices. Now we've got choices. We can change the RTL, which is possible for my code that I've written. It's not possible for the Smart Connect. It's possible for my code. We can use different synthesis options. We can add timing exceptions. We have to think about what we want to do. So in this instance, looking at the Smart Connect with the register here and the register over here, and there's a long routing delay in between. There's a long routing delay in between the two. I decided to leverage something I talked about in my previous webinar, which is the concept of putting flip-flops as a wrapper around the cores. Now, I didn't want to go away and write wrappers for the cores. So actually what I did, and I don't know if it's on the next page, it is perfect, is I actually inserted a register slice in between the Smart Connect and the block RAM controller. That means that kind of breaks the path between what the Smart Connect, the routing between the Smart Connect and the block RAM. So it means we get more margin in our timing window, because there's now a register in between, breaking up that path, that long route across the design. So we drop that register in AXI register slice in there, and then I reran the synthesis again to make sure that by putting this slice in and then running the optimization again, that problem had been addressed and removed. And it had. If we run the timing again, and all these projects, like I say, all these projects will be made available to you on GitHub, so you can go take a look. It had. So now we're stuck with the code that I've written. We've still got some failing paths in that code. So the only real option at that point in time, and that's the failing path, and you can see there's lots of logic levels in there. The only real choice we've got is to make some changes to the RTL. So this is what I did. I made some changes to the RTL. I added in an extra stage in the state machine to give me some extra time, because when I analyzed the design, I was being a little bit too fast. So we ran it through, and I added this change. If you want to sort of see that and review your RTL and see what the tool thinks of your RTL, which you should do, it doesn't always pat you on the back and say, "Great job, Adam, you've written this code really well." We can run the quality of results assessment, and then that will give us a score, and it will tell us what to look at and what to think about with our design. So it'll tell us where to go away and think about, to go away and look at our RTL. Which is always quite useful. So the issue in the custom RTL, and you'll get the custom RTL, so you can go away and look at it and laugh at it and go, you did that the first time around, is we're receiving 4 bytes that need to be packed into a 32-bit AXL word. If we needed to modify that and check that we made sure that we got all of the 4 bytes before we moved on and did anything. So what we could do is we could remove the code. No, that's not really going to work for this example, and probably not for most, because it'll never work. It's not going to work and not do what we want. We could modify the state machine, which is what I decided to do, or we could have defined a multi-cycle path constraint, because That might have been okay in that case, but to be honest, it's better to do the sensible thing and to fix the design by modifying the state machine. So this is exactly what I did. I made some changes that once we'd got all the data in there and we got all the bytes in there, instead of making the immediate decision what to do, we'd go to another state, we'd check that it was at the right length, we'd got everything was good, and then we'd move on to the next state. So you can see here is the original code versus the modified code on the left hand side. Just to show you the difference, the state machine, if you're a graphical person, there's two state machines showing, and you can see we've implemented this new check write payload state just to make sure that we do this. We're now in a state where we're in a pretty good position, I think, that we could then rerun the synthesis, rerun the optimization, and we should see when we report the timing, we should see no timing issues in the tool. We get some warnings, but we don't get any timing failures. So this is looking quite nice at the moment. We've found some issues. We've found them early. We've not waited until it's gone all the way through implementation. We have this. The next stage then is, if you remember from the stages that we're going to go through, the next stage is to run the place design. And once we've run the place design, and then we report the timing again. Rather luckily, and I swear I didn't plan this because it's quite difficult to make timing failures. When you want to make timing failures occur, it's quite difficult to make timing failures occur. When you don't want to, they occur all the time. But when you're trying to create them for a webinar, it's quite a challenge. But rather luckily, as it would happen, when we did the place, and then when we do the report the timing again, we see this time we've got some hold failures. But we can look at these hold failures, and they're actually less than the 0.5 of a nanosecond that we have to look at and investigate and try to correct. So in this case, following the guidelines of what to do, I decided that I wasn't going to do anything with these, and what we would do is we would run through and do the final bit stream and generate the final bit stream of the FPGA. And as we were running through, what we saw then is that router is available to adjust routing such that it can address those small hold time violations. And what popped out of our design is what popped out of the routing stage is a design then that meets timing closure. For the baseline timing closure, obviously we've still got the I/O to do, but it gives us a simple baseline timing closure. We've addressed any issues in the design. We've checked any methodologies any issues in the design with methodology, and we've now got a very simple set of rules that we can use to go further forwards and achieve the timing closure, looking at the I/O. So to achieve this baseline, and like I say, I'll put 2 or 3 projects up on the GitHub that get shared with this. So check back on my website later on, and you'll be able to see these projects. We've used the constraints wizard to define that initial timing constraints. We've corrected any methodology constraints violations that have come up, with that insertion of the buff G. And then we've addressed the timing violations in the RTL and the smart interconnect by, at the end of synthesis and at the end of that optimization phase, we've gone through and we've done that relatively simply. And then we've allowed the small hold violations. We have allowed the router to address those. So the key takeaway to this, I guess, from a lot of this is it's a very simple process. It's very easy to do. But the main thing is we addressed a lot of these issues before we even got to looking at the place and route. We did a lot of these just off the back of the synthesis and the optimization of the design. So this base level thing we can do. King, give me 1 second. I will answer that. So if you want to look at some advanced concepts for this, if you're doing it, and timing closure can be quite challenging. We could look at block level synthesis for different synthesis options in different modules. We can look at optimizing the levels of logic, and we can look at pulling back the levels of logic and pipelining them, as we showed in our previous webinar. And again, we can look at reducing control sets and optimizing high fan-out networks, again, which we looked at in our developing RTL for time enclosure webinar a couple of weeks ago, and it's also on our website. User Guide 949 is a great place to get started with this and running through with it. So a couple of comments to think about for wrapping up for the conclusion, and then we'll have a couple of minutes and I'll try and go through all the questions people have asked, because I've been not looking too much at the questions. So we should think about, obviously, like anything, we should think about timing from day one, and we should particularly plan the clocking and the clock networks. We should make sure that we're following the Ultravast Design Technologies Guide to get the best possible start for making sure that we get time enclosure. And we should establish this base time enclosure immediately following the synthesis of the tool. We shouldn't just do synthesis and then click on implementation. And we should leverage those reports to make sure that we get the best we can do. Paul, that's a great question. I was just going to answer that and say, yeah, the QOR results you can open from the implementation, the implemented design. I think the earliest point you can open them up from is from immediately following the optimization process. So you can run through that and immediately get it following the optimization process. So if anybody has questions, I hope this has been useful to everybody. I hope this has been really quite nice for people to do. I think it's unusual to have a webinar where you kind of walk through and talk about sort of here's how to get to a time enclosure point. And I will, like I say, the projects will be made available on the GitHub. So someone's asking, what constraints would you add for a relatively slow protocol like I2C? For the I2C, you've got to basically do the I/O timing and analyze the I/O timing and make sure that you capture make sure that you capture the element, make sure that you capture safely the data. Now I2C is relatively safe because it's really slow. And I'm just trying to think, actually, I did an I/O timing example of an I2C actually not long ago for a ESA mission. So if you're familiar, Damien, with my website, I'll put up an example or something showing how to do that timing through it. But it's basically, you just need to consider that you need to consider that the I2C data is safe when you do that, when you sample it, which it should be, because there's just so much margin. But you've just got to consider the clock to out, the tracking, and any additional delays. But it's relatively simple. Ludwig, yeah, if you go to my website, and I will type this in here, just so as people can find it, adiuvoengineering.com. There's a webinars thing along the top. If you go looking at the webinars thing, or is it workshops, webinars, workshops, you will find in about an hour or so's time, I'll upload this. I'll upload links to where the presentation is. You'll be able to watch a replay of the video, and it will all be there. Let me take a little bit of a look through the questions, because it was quite busy today, and we'll see if anything else. But if anybody's got any questions, please pop them in. Michael, I'm not really sure what you mean. Michael McLeod, I'm not really sure what you mean by a range of, say, 1 to 120 meters a second, for example. We tend to measure clock frequencies in megahertz. I don't have any spooky clock stories for Halloween, and I when I planned this, I didn't realize it was Halloween. If I had, I might have dressed up as something. I have we have the Spartan helmet on the desk here, for everybody. So maybe I should have started out wearing the helmet, But yeah, no, thank you everybody for coming along. We have another one, actually. We have another webinar next week, which is on the 7th, which is looking at how you can do maths in FPGAs. So in that one, we're going to take a look at sort of like fixed point, floating point, how we can do complex maths, how we can do things. I think it's going to be a lot of fun to go through. I like doing maths in FPGAs. And then we have one at the end of November on sort of mixed signal, working with ADCs and DACs and such like, based around FPGAs. So yeah, I'll wrap it up there. Thank you all for your attendance as always. And please reach out, let me know if you've got any questions or comments, and we will take it from there. So thank you very much, and yes, I'll see you all soon, I hope. Bye bye.